Sam's getting it.
All right, we're on.
Why?
It's on.
Aren't we doing the problem though? Don't we have to wait until we're done doing the problem?
Show them the problem.
That's the problem, guys.
New planet has a density 2/3 of the density
What do I do to
of
say?
Earth
Oh, here's
and a
plenty of
radius
space.
of twice the radius of the Earth. What is the gravitational field? And it's an interesting deal because, and this is, again, the AP boys. So it isn't like...
Sorry, hold on. Just go on.
Yeah.
I'm sorry.
Because they don't give it to you in values of like meters per second squared. But if you think about it, I mean, it's kind of cool because if you look at the gravitational field on Earth, what's the strength of the gravitational field on Earth? Yeah, 9.8 newtons per kilogram. Because okay, it's 1 kilogram mass. Okay, that force is 9.8. If you have 2 kilograms, it's 19.6 newtons. So it's like a linear function. So the other thing you can do is go, oh, well that kind of flips me out. Well, newtons are kilograms meters per second squared divided by kilograms, and kilograms cancel out. You get meters per second squared. So.
Forgot about that.
Okay.
Extra 2 down there.
Something to think about.
Are they gonna like make us delete our calculators before we go in?
I don't know. How about that?
Okay. I'd rather not because I have all these variables saved in them.
Stored in them?
Got it wrong.
Yeah.
Huge.
You square it?
Yes.
Well, I guess I can turn this thing.
What's the right answer?
I'm pretty sure it's D.
D.
It is D.
Yeah!
I got it right when I did it wrong. Because I squared R and then I didn't square R. I squared it instead of cubed it, and then I only did it times once, so I got 13. So I was like, wait, this is wrong, and then I got 26. And then I got 13 again because I did it right, correct, the last time.
Okay.
Where is everybody?
Which Sam, that makes absolutely no sense. So let's talk a quick review of gravitational fields. Okay? So here's GDE, right? And so if we want to find the gravitational attraction between
She
GDE
also
and
weighs
the
more
Earth,
than Kyle.
we can take every particle.
We are not doing this again.
She also weighs more than Kyle.
Stop that.
Hey, Sam, you shouldn't be talking either.
We should not do this.
Yeah, I was just
No,
going to say.
yeah.
I haven't said anything.
Okay, anyway, shh. Okay. So this all hinges from Newton's equation, big G, m1, m2 over d squared. So option number 1 is that we find a proton in the end of your finger and we find the attraction between that proton and the entire Earth. And we get done with that proton, then we go to the next proton beside it. We do the same calculation. It's going to take forever, not going to get anywhere. Screw that. So the other option is that we treat Emma as a point mass and the Earth as a point mass. Okay. So we'd have big G, mass of the Earth, mass of GDE divided by d squared. Long, arduous process, it'd work. Mass of the Earth, we know the distance because we treat them as point masses. There we go. Or we can just go, oh, FG equals the mass of GDE times the gravitational acceleration. Much simpler. 1 kilogram, 5 kilograms, whatever it is, we slam it in. But here's the whole key. This equals big G, mass of the Earth, mass of GDE over R squared. So, what's going to happen to Emma? Sorry, Emma, if you ever watch this. But you cancel out
She
the
doesn't
equation.
matter.
None of you do.
So you're right.
So here's
But
the
some don't matter more
ramifications
than
of this.
others.
You get little g equals big G mass of the Earth over R squared. Henry Cavendish used this equation to find the mass of the Earth, because we knew the radius of the Earth, we knew that G was 9.8 meters per second squared. He had figured out big G at that point because of his experiment with the lead spheres, and he was the one that has the claim that, hey, I weighed the Earth. Okay, cool.
Is that a big scale?
That's a big scale.
Yeah, it was just floating out in the middle of space, and he grabbed it and he like set it under Earth, and there you go.
Boom.
What dunked it?
No, they sit it on top of Earth.
Went boom.
Oh yeah,
Okay.
because that's actually south.
It was
So-
the South Pole and just.
Yeah.
Now, there's a couple ways that if you look at this problem, what's one thing that you could do to get this?
Find the new
You
mass.
could write the.
You could do absolutely smash mouth physics.
Lame.
You could. I'm just telling you, you could, right? If you have to store it in your calculator, the radius of the Earth, 6.3713 times 10 to the 6th, okay? Mass of the Earth, 5.979 times 10 to the 24th, but you got to have the density of the Earth. To find the density of any object, what do you need?
Mass and volume.
Mass and volume, right? So I could do the ultimate smash mouth thing. I could find the density of the Earth by using, okay, that density is mass divided by volume, which is going to be the mass of the Earth. Now, how do you find the volume of any sphere?
4/3 pi cubed, not squared.
Yeah.
4/4 pi r cubed, right? And if you have this number, right, stored in your calculator, and you have the masses that are stored in this thing, you could find the actual density of the Earth. You could multiply that by 2/3, and you could get a number, okay? So that would get you this. Then you'd have the radius of the Earth, right? Now, then the whole key to this is to go back to this, big G mass over r squared, okay? And if you know that density is 2/3 of that, you could find the mass, you could find the radius, and do a whole bunch of math physics, and you have 50 questions to work on this section, and you're going to spend 10 minutes working one problem.
Woohoo!
And then you're going to run out of time at the end, which is bad. Well, what's another thing that you could do? Nicola, how did you approach it?
Well, I found the new mass in terms of the mass of Earth.
So how did you do that?
Well,
Well,
mass equals density times volume.
yeah.
So you know the
So
new.
rho v.
Yeah. So you know the new density is 2/3 times the original one, and you know the new volume is 8 times the original one
Why is it 8?
because it's r cubed, 2r
Right.
cubed.
So because of this is r cubed, and this is twice, you know that volume, that's the whole key to this. So that volume, that radius, because it's cubed, becomes, that volume increases by a factor of 8. Okay, so right away, that's a huge determining factor. So that volume, basically this would be like a big gaseous giant. So here's the original Earth, right? So this is going to be r cubed, which is going to be 2 times r, which right away is going to get you to 8. Okay, well that's a huge deal. So if you look at that equation, the little g equals big G mass of the Earth over r squared, okay? All right, so we got a big volume, now what?
Okay, and you multiply that by the 2/3 density thing, so you get 16/3 times the mass of the original Earth,
Okay?
and you can plug that in over there. And so,
Plug it in over where? The little g
no, the m,
for the n?
yeah,
So 16/3?
ME.
16, which is like 5 point something.
I don't know, I just left it as that.
Okay? Then what?
And now you have to take care of the radius on the bottom there,
Yep.
and that's 2r, so you end up with the 4 down there.
That's 2r squared, so we get 4 there.
Then you have 16 thirds divided by 4, which is 4 thirds. Then you multiply that by g.
And you get
13.
13. Okay. Much cleaner way than doing the smash mouth physics. So anytime you see an R in there that's squared, cubed, focus on that. That'll right away kind of lend itself towards what's going to happen. Okay. Got that. We're cool. Okay. So let's start with, there's basically a projectile motion problem, there's an energy problem, and there's a spring problem. You want to do the one that requires most thought first or most thought last?
First.
First.
Okay, that's probably the 2008 question with the springs. That one requires probably the most thought. So give that one a try.
What?
Where do you start? You got a force, you got two masses.
I found the acceleration on the big mass first.
As if there were no other mass. As if the 2 kilogram mass didn't exist. That's what I did.
Wait,
Uh-oh.
I found the system.
Guys, here's the key. It says they're both equaling constant acceleration. Okay? Now, when you first accelerate this thing, you know, if you were just going to pull this, you know, that string would stretch and then this would actually, you know, then kind of catch up to it. But because, and that's the whole, these three words are the whole key to this problem. They are experiencing equal constant acceleration. So both of them have the same acceleration. Because, yeah, initially, if you just jerk the first one, that string's going to stretch out. Okay? So, if you look at F equals ma, they're both experiencing the same acceleration, right? So, the only available force is the 4 newtons. So, treated as one system, then you got F equals ma, so you take those 4 newtons and divide that by the combined mass of 10 kilograms. Now, but that's not your answer. It's part of your answer. Because then, ultimately, then it says calculate the force of the spring exerts on the 2 kilogram block. So you're trying to find the force that's going to be exerted here. So since the whole system is accelerating as 0.40 meters per second squared, now you do F equals ma again. Now you're trying to find that force. So, okay, well, now it becomes simple. It's like, okay, I got a 2 kilogram mass. It's accelerating at 0.4 meters per second squared. So then it's just a matter of using F equals ma a second time by taking 2 kilograms times 0.4 meters per second squared, and you should get 0.8 meters. Thought you got caught?
Yeah.
Nice.
I got 1 centimeter for extension.
What'd you get?
I got 1 centimeter.
Yeah. Sean.
I started it like that, and then I started thinking about it too much, and then Nicola had it the other way, and then I need to sit away from Nicola.
John had it the other way too.
Well, I started doing it that way, and I was like, wait, why?
So it's like, hold on, it should be the same. It
Guys-
should be like they're a thing, because what else is it's like that's not how things work. But then problems. And
Well, it's also a frictionless surface and everything else. So, I mean, it's very much an idealized situation. So, and the beauty of it is because they are both undergoing the same acceleration, okay? Now, then calculate the extension of the spring, right? Okay? Well, you've got a spring constant of, what is it, 80, which is fairly established spring. So then you go, I think this is why Kyle, you were asking this, so for part B, you have F equals Kx. Well, look at it this way. If they were just sitting there, and even if they were moving at constant velocity, okay, if they were moving at a constant velocity on a frictionless surface, what would be the extension of the spring? Yeah, there wouldn't be any. Because if it was a frictionless surface and they were already moving, the spring wouldn't have to exert a force back here. Because it would just move up its own accord. Okay, and there wouldn't be an issue. So, you know your force at this point is 0.8 newtons. And so you're trying to find that. So you got F divided by K equals X. So you got 0.80 newtons divided by K of, what was K, 80 newtons per meter, and you get 0.010 meters, which is all of 1 centimeter. So it's not going to stretch it very much at all. Good with that. Okay. So if you work the second part?
Yeah.
Okay. So now we're going to pull it to the left. So what's going to happen to the acceleration?
Should be the same since the system.
Oh, still the same. John, you racing?
Yeah.
Oh yeah, I guess if you didn't work it as a system, yeah. So it's going to have the same acceleration because it's still 4 newtons, and it's still undergoing equal acceleration. So it's still going to be the same. Now, is the amount of the spring stretched less than, greater than, or equal to before?
Greater.
Why? Since you seem to own this question, there, Ostrich.
Well, because it requires more force to accelerate the bigger block.
Yeah. So it still has that same acceleration of 0.4. So then if you go back to this equation, it still has that exact same acceleration. But now instead of 2 kilograms, now you're going to use that 8 kilogram. So this becomes 1.6 newtons. So then you're taking 1.6 newtons and dividing it by 80. You're going to get a greater stretch. Good with that?
I got that right, yes.
Okay. Now, the beauty of E is that you don't have to have answered A, B, C, or D up above to do E. Literally. E has nothing whatsoever to do with the problems up above. It's a completely new ball of wax. So, how are you going to approach E? Momentum standpoint, energy standpoint, both, neither? Sam?
Energy.
What type of energy did you have before? Before it hit the wall, what's the only type of energy that you had?
Kinetic energy.
Kinetic energy. So, the whole key to this, okay, is that you want to calculate the maximum compression of the spring. So what's going to happen during the maximum compression of the spring? What's going to happen to the velocity?
Maximum compression, it goes to 0.
Yeah, the velocity goes to 0. So all of the kinetic energy that you have is stored as
Spring potential energy.
spring potential. So the kinetic energy is going to be 1/2 mv squared. And that's going to equal, here's where that 1/2 comes into, 1/2 kx squared. Now, here's the $1 million question. Block A hits first, sticks to the wall, calculate the maximum compression of the spring. Here's the $1 million question. What do you use for the mass? 2 kilograms, the 8 kilograms, or the 10 kilograms?
8.
Why?
Because that's the one that
what's
compresses
moving.
the spring.
Yeah, because that's the one that's still going to be moving and will make that thing compress, right? So basically you set them equal to each other, the halves cancel out, and you get mv squared divided by k, the square root of that, and you get x, and you should get 0.16 meters. Good with that. Okay. We'll save the easy one for last. Speaking of energy, let's talk about the 2014 one with the tree.
The tree.
Who did this one?
Yeah, I dug into the archives for this one. So, here's the important part on C, right? Let's go to the rope, right with C, draw a solid line to represent the trajectory. So,
It's still moving up.
when you drew this,
Going forces down.
roughly what did
But
you
it's
get?
still moving up.
What, Kyle, what is your line for A look like?
I drew a line, I was just going down.
Just like this?
Yeah.
I think it goes up a little and then down.
Or like this?
Sure.
Could you have this?
No,
Why not?
because you don't have enough energy. You can only go up to the same point you started at.
Exactly. So no matter what you draw, don't take it above D. Okay? So, yeah, realistically, you're going to have some projectile motion, okay? But whatever you do, don't cross the D threshold because of the fact that you would have gained energy, which would be bad. Okay, realistically, with air resistance, you're going to end up below D. Less than D.
No,
No,
not at all.
It's way over D. It's almost over the dotted
It's
line.
almost the tree branch, actually.
Yeah.
Then it goes backwards.
Yeah.
Does a loop.
We can add that in there, sure.
That's what happens when you go this.
Okay. Now, D is an interesting one. Dash lines represent the trajectory of the center of mass at D. What do you have there?
Straight down.
Straight down. Because at that point, they're at the highest swing, everything is just potential energy. It's just like dropping it and it goes doink.
There's no velocity.
The exact noise it makes is doink. Okay. C is pretty straightforward. An UG calculation, you're either going to get 2010 or you're going to get 2050,
Okay.
depending upon which one. It's just MGH.
This is supposed to be 2000. It's 2009.
Now, let's talk about C. Center of mass at point B, lowest 2.4 meters above the surface of the water. Calculate the person's speed at point B. Okay? Now, so here's the deal with this one. How far is the person actually going to fall? I mean, from, if you look at that, right? So, you're 2.4 meters here, right, above the water. And the person is
Oh, I made a mistake.
4.1 meters above here, okay? So the difference between these two is just going to be 1.7 meters. Now, here's the cool thing about this. Could you use that equation?
Maybe. I don't know. I did energy.
Yes, because it's gravity.
Why?
Gravity.
Okay, here's the deal. Because at the top it's all kinetic energy, at the bottom it's all potential energy, right? And that's where that equation comes from.
Wait, you mean that backwards?
Yes. Yes.
V squared equals V naught squared plus 2AX, right?
No, you said that at the bottom it was all potential energy.
Oh, I thought you were talking about what I wrote here.
No,
Yeah, at the bottom it's all kinetic and at the top it's all potential. So the path that it takes doesn't make any difference. Whether I drop it straight down or I swing in an arc doesn't make any difference. The amount of energy that you have here is going to determine that. So whether I drop it or it swings in an arc doesn't matter. Now, you can do the energy thing. You can go, oh, kinetic energy equals 1/2 mv squared, and then set that equal to UG, which is mgh, okay? And you end up with the exact same equation because the masses cancel out, and life is good, and you get 5.8 meters per second. Now, you're not asked this question, but they very easily could. You got a 50 kilogram person. At this point, they're moving at, what was it, 5.1 meters per second? Something like that. What would be the total tension on the rope at the bottom of the swing? How would you find it? What's the minimum, even if you're just hanging straight down, what's the minimum amount of tension that's going to be on that string?
FG.
Call it 10, 500 newtons, right? So at a minimum, if they're just hanging there, there's going to be 500 newtons. But what else are you doing?
Circle.
You're making it go in a circular path, right? Which is then going to require centripetal force, and assuming this person doesn't have a negative charge and they're in an external magnetic field that would create that, let's go with the idea that that rope's going to have to make up that difference. So basically, if you were asked to find that total force at the bottom, it'd be Fg plus your centripetal force. Now, if you really wanted to get clever, you go, oh, that's mg, that's mv squared over r. You could factor out an m and go, oh, that's g plus v squared over r. Makes it a little bit easier, doesn't make any difference. So, but anyway, that's how you do it.
Can't tarnish the KGB.
Okay, it's like the take sign, you're on third base.
All right, Putin.
Okay. Oh, don't joke about Putin. What, they just rushed past a law like you can't put Putin's face on like a clown picture and post it in public or something. It's
Probably something dumb like that.
Keep it on there, though.
Can you put it on Donald Trump though? Oh, clown Donald Trump.
Political humor.
So what'd you get for D there?
4.
Four-ish, right?
4.0.
So the whole key to that is that you have to figure out how long it's in the air. So if there's one handy equation with all things that are fall, assuming that they're dropped, it's this handy dandy little equation that you have 2x over g, which comes from 1/2 at squared plus v naught time. Does it make any difference at all that they are moving horizontally when they let go of the rope in terms of this calculation? No. Why?
Because it's in the Y direction.
Yeah, this is acceleration in the y direction. What happens in the x stays in the x. What happens in the y stays in the y. So you get a time of 0.70 seconds. Multiply that by the 5.8 meters per second from up above. You get 4.1 meters. Then you want the momentum at PC compared to the momentum, speaking of politically correct, the momentum at C versus the momentum at B. Which one's bigger?
E, because they zoom in.
So help me God, if you write that.
Because they zoom in. I don't like how this next question wants a clear, coherent, paragraph length response.
Yeah, that's pretty lame.
Wait, let's write an
With the
explanation.
projectile motion one? I promise you, they are making you write more and more on these tests.
Here, please write a new Bible
Like Y.
about
So
this
English-
question.
Because it's this new age thing, oh, it isn't about calculations, you have to make them right, and all of this other, and everybody that's grading it going, screw you guys, you grade it then.
Strike.
Do math and find out if the answer's right. Okay, now, so let's talk about this one. This is the easy one, the one with the projectile motion problem. So, it's an interesting thing though. On A, here's the dots, okay? Free body diagram showing and labeling the forces. So, B's shot off, A is falling straight down, you're at halfway through the flight. So, here's A, here's B.
Softball.
A lot of people miss this actually.
Wait.
I was saying, if you look at the national and all the, I was surprised at how many people got it wrong. So what's the only thing you've got?
Well, don't sleep on force buoyancy.
Yeah. Will they count you off
You're
for
right.
force buoyancy?
They couldn't. So that's right.
Yeah.
Checkmate.
They're looking to give us points, not take them away.
It does say air resistance is negligible.
That's not points.
So I know, but I just don't. Okay? So what's the difference between the one that's dropped and the one that's thrown off?
Nothing.
Nothing.
Absolutely nothing. Okay?
No, that force of gravity is like
Oh, yeah, that
angled,
one's
angled
kinda like
45 degrees
angled.
that way.
Yeah.
Yeah. Kind of like this?
Yeah.
Okay. So what do you have on B?
2 straight lines.
A is at 0, B is above 0.
Yeah. So you have two parallel lines, A's at 0, B's horizontal line, the human line or the human ruler.
Oh, these are not even lines.
Here, I got this.
You got it?
Yeah, these aren't good lines.
Yeah, between Trout being the human scissors and you being
Humans.
the...
I'm human office supplies. I've done a couple things.
He's
Okay.
not a one-hit wonder.
Yeah, Sam has diversity on his side.
Yeah, Sam's
He's
not
Hispanic.
a one-hit wonder.
Heck
like some
yeah.
people.
All right. Now,
Straight.
now, see, here's what, again, I've talked about this and I've talked about this. Here's my concern about C, is that they want to give you points. And you're just going to think, this is just so simple. It's like, well, duh. And that's what you're basically going to write is, well, duh. And
duh.
you're going to know a whole bunch of complex physics, and you're going to miss the duck points. Okay? So if you look at this, explain why the spheres reach the ground at the same time, even though they travel different distances. So here are the things that you had to mention. You had to mention that Vx had no effect on the time. Okay, that was one of the things that you had to mention. You had to mention that they both had the same initial vertical velocity. Okay?
That was implied.
They do this.
And like height.
What if
and,
it's
like,
implied
force.
by your equation?
No,
God.
Wow.
it says clear, coherent, paragraph length response.
Oh, that's dumb.
Don't write C equation.
See physics.
Do they
that's-
both
that's
undergo the same vertical acceleration?
Yes.
Yes, you need to mention that. Now, here's what I found odd. 1 point, even though this is, and I just found it odd that you had to say this to get 1 point. 1 point was that you, for literally, I'm not making this up, 1 point was within this, and then you had basically had to say, and they hit the ground at the same time. There was 1 point for saying that they hit the ground at the same time.
You had to
Got
agree
it.
with the question.
So,
So that
explain
was
why
for
the
4
spheres hit the
points.
ground at the same time. Because they hit the ground at the same time, and you get a point.
Yes, that was one of the 4.
Yeah.
They get
I'm
there
doing
at
just
the
that.
same time.
Basically, like,
So, literally, it was 4 points. 1 point for saying the horizontal velocity didn't affect it. They have the same Vy, they have the same acceleration vertically, and they're in the air the same amount of time. That was with the 4 points. It's like, you tell them that they hit at the same time.
and you tell them the Earth is round.
Don't even get me started on that.
And you tell them just focus on the reason, don't focus on.
I know. I just want to go to the people that write these and go, seriously? You lay awake at night trying to write stupid questions?
Burn.
Anyway. Okay, let's go home. Been a long day.